So, hello everyone, and welcome once again to the Latin American webinars on physics. I'm Joel Jones from the PUCP in Peru, and I will be your host today. This is webinar 189, and we are having José Jiménez as a speaker. José is a postdoc at the Department of Astrophysics in the Brazilian Center for Research in Physics, although currently he's on a research stay at the Institute of Theoretical Physics of Goethe University in Frankfurt. Originally from Peru, José did his PhD at the Federal University of Rio de Janeiro, followed by a first postdoc at the University of Sao Paulo. All of this in Brazil. Today, José will tell us the latest news in QCD phase transitions in the context of neutron stars. So we are very happy and excited to have him as a speaker today. Now, before we begin, let me remind the viewers that you can ask questions and make comments via the YouTube live chat system. And these questions will be passed on to José at the end of the talk. So having said that, let me now give the microphone to José.
Okay, thank you, Joel, for the nice introduction. And I would like to thank also Joel again and the other organizers for the invitation. And I'm going to share my slides. Can you see them?
Yes, perfect.
Okay. And as already Joel announced, I'm going to talk about QCD transitions, especially using this kind of neutron star called twin stars. And most of the results which I did for this presentation, I did with my collaborators in Brazil, Lucas Lazari and Victor Gonçalves from Federal University of Pelotas, and also Camila Rodriguez and Ignacio Ranea Sandoval from Universidad Nacional de La Plata in Argentina. So, this is the online of my presentation, and I'm going to give an introduction because I understand that there are some technicalities which most of the people doesn't know. So I'm going to make sure that you all understand the basics. Then I'm going to summarize also the ideas about twin neutron stars. Okay. And after building the formalism, I'm going to develop also the formalism for radial and non-radial oscillations, and which is important to determine the stability and also these G modes. And then I'm going to present results for this QCD trace anomaly, which is a relevant quantity in the last years. And then results also for the behavior of this so-called discontinuous G mode, which is associated to the discontinuous phase transition, which happens in these twin stars. And finally, I'm going to give a summary. Okay, let's start from the basics. I think that all of us, we have seen this beautiful image, the so-called Crab Nebula. And it is beautiful because you can see many colors, you can see something like an explosion and all that. But I think that as physicists, we can go forward and we can ask what happens with this event in other sectors of the electromagnetic spectrum, okay? And for instance, NASA has these beautiful images in the optical, which is this one, which is the famous one, optical region of frequencies. And we can have also images from the radio sector or the infrared sector. But for this talk, we have to focus on this X-ray image where we can see that something is creating a disk, okay? And this something is a rapidly rotating object. And this object is more or less of the size of a city, more or less 15 kilometers of radius or 20 kilometers of radius. And the question is, what is there? Okay. And what we know today is that there lies the so-called pulsar, which comes from the name pulsating source of radiation originally. And of course, in this image, we are not in the same scale. You can see here the Earth and here the pulsar. But the main idea was to extract the information from this pulsar, which is an object of 15 kilometers of radius, more or less. It has magnetic fields. It has an axis for rotation, okay? And also in this rotation, it emits radiation which arrives the Earth, okay? So the idea would be to understand this object, the so-called pulsar, which astronomers has a lot of thousands of information since the late 1960s, 1970s. And as of today, we have information about the masses of these pulsars. And for instance, in this uh, table, we can see that there are many observations depending on the source. For instance, sometimes astronomers have detected these pulsars in binary systems and binary systems of neutron stars, which is the technical name for these objects, and also binary systems composed of white dwarfs and neutron stars. And okay, these binaries exist because, as far as we know, most of the stars in the universe live in binary systems. Okay, so at the end of their evolution, they will end also as binaries. And you can see that most of these neutron stars, they are around the, they have around a mass of 1.4 solar masses. So there are some of them which has higher masses. And of course, there are extreme situations where the masses even reach this sector, for instance, two solar mass, two solar masses. And the question would be, as theoreticians, what is happening with these objects? What is their stellar evolution, their formation, and all that? So we can uh, go to our books about the cycles of life of usual stars. And for instance, our sun, which is an average star, this star, after billions of years, will become a red giant, and then it will develop a planetary nebula. And as we know, our sun will end as a white dwarf. And this is because the mass of the progenitor, our star, is not too heavy. On the other hand, other kind of stars, heavier stars, they will suffer a different kind of process. And for instance, after the hydrogen uh, is finished at their course, it will become a red supergiant, and then it will suffer this so-called supernova stage. And after the supernova, two things can happen. This supernova will produce a black hole, depending of the mass. For instance, if the mass is about 20, 25 solar masses of this massive star, and if not, if it is between 8 to 20 solar masses, many detailed numerical simulations have proven that these supernovas will lead to the so-called neutron stars. Okay, as I told you, neutron stars are our theoretical object because we can simplify the study of these objects, which are small, but they have a lot of mass, right? Even they are even more massive than our sun because as you have seen, most of them, they have 1.4 solar masses. And neutron stars, you can add the different properties of a pulsar, magnetic fields, or you can add the effects of rotation and all that. But we can start with a simplified version of these neutron stars. And for this, we have to use the Einstein equations. And we can assume that these stars are spherical, they are static, no rotation, and also the composition of these neutron stars could be made of a non-dissipative fluid, an ideal fluid. And this ideal fluid, as we all know, is related to this energy momentum tensor, okay, where P is the pressure and epsilon is the energy density, U is the force velocity, and G mu nu the metric tensor. And since we are assuming that this star is spherical asymmetric and static, we can use a kind of space-time metric similar to the Schwarzschild one, okay, where this lambda function and nu function are the metric functions, and they are changing the way time and space is around this star. And the first one who solved this Einstein equations for this scenario were Tolman in 1934 and also Oppenheimer and Volkov some months before the start of the Second World War. And in, they derived this pair of equations for the pressure, for the gradient of pressure, and also for the mass of this star. And I separated here in black the Newtonian hydrostatic equilibrium equation, okay? Because in this system, we are saying that the perfect fluid has pressure, and the pressure as a gas, it wants to expand. On the other hand, the energy density, it, it is related to the energy content of the whole star, and generically, it favors the collapse. So there is a kind of competition between an expanding gas and a collapsing star. And if we use general relativity, we will get these corrections, these terms in red, which are associated to the space-time curvature. And it can be proven that these equations are nonlinear because you can see here a square term of the pressure. So these equations are more complicated than the Newtonian version. And here, m, from the Newtonian point of view, would be the mass contained in this uh, sphere, this star. But in general relativity, this mass, you have to remember that it is called the gravitational mass, not the usual mass in the Newtonian sense, because this mass not only contains the rest energy of the particles composing the star, but it also contains the gravitational energy in the system. In the Schwarzschild formulation, we can separate these terms, but this is very delicate in more realistic scenarios, for instance, when the star has rotation or magnetic fields and all that. So in our case, we can display a clean interpretation. And these equations should be solved as every differential equation imposing boundary conditions at the center. We can say, okay, we have some value of pressure at the center of a star, and at the center of the star, we don't have nor energy, nor mass, nor rest mass. And we have to stop our integration until the pressure goes to zero, because this point indicates the surface of the star. And then we can evaluate this gravitational mass at this radius, and we can have the mass of the star. So we can extract information about the mass and radius of these neutron stars using these equations. And to solve them, we need what is called the equation of a state. Okay, pressure in terms of energy density, or energy density in terms of pressure, to have two equations and two unknowns. And the microphysics is encoded in this equation of a state. Okay, for instance, the first result of Oppenheimer and Volkov, they solved it for a relativistic degenerate gas of neutrons. And when they solve the TOV equations above, they plot this mass and radius diagram. And you can see the behavior at larger radius related to low densities. And as we go to the left, we are increasing the central densities until we reach a maximum, which is the maximal stable configuration, because it can be proven that if we continue going to the left, we have unstable stars which are going to collapse into a black hole. But you can see that here the maximal mass is about 0.7 solar masses. So, but some slides before, I told you that most of the observations favor 4 solar masses. So we need to include interactions, because this model is very simplistic, and also new phases to reach those values of mass. Okay, and as I told you, there are observations which favor neutron stars with 2 solar masses, or a little bit about 2 solar masses. And also there are other data for 1.4 solar masses, or a little bit about. And these curves represent different equations of state. Okay, and you can see that, for instance, some of these curves, blue curves, they will not pass through this orange region. So it is a way to say that these models for the equations of state cannot be considered realistic. So we have to forget about them, or maybe change the parameters, or maybe get another type of information to constrain them. But the idea is that all these equations of state have to pass through this canonical observation, okay, of two solar masses. Recently, also we have information, X-ray information from this detector called NICER, this Neutron Star Interior Composition Explorer, where you can see in this plot mass radius diagram these ellipses, right? This diagonal ellipse and this horizontal ellipse. And the center of these ellipses are the values measured for the radius of some pulsars. So there is information for pulsars at about 2 solar masses, and there is information for the radius of some pulsars at about 1.4 solar masses. So we have to take care and tune our models, the parameters of our models, to have consistency with this data. And if we do that, we have to include new phases, new macrophysics in these neutron stars. And you can see, for instance, in this object, that at the crust we can have iron. And as we go to higher and higher densities, or to the interior of the neutron star, we can have complex and complex phases. Okay, for instance, superconducting protons. And at the core, we can have also pion condensation, kaon condensation, superconducting quark matter, or ampere quark matter, or many other phases, hyperons, and all that. So all these content of different degrees of freedom should be encoded in the equation of state when solving the TOV equations. And for instance, in this plot, I'm displaying the pressure versus density, or energy density is the same. And all these curves represent different microphysics. Okay, if you change only a degree of freedom or a coupling in the Lagrangian, which is useful to derive these equations of state, you can have different behaviors. So you will have many curves. There are thousands of models. But basically, the idea, for instance, in this case, at low densities, is that low values of pressure, or low values of density, or from the formal point of view, low values of quark chemical potential, they mean that we are close to the surface of the neutron star. As we increase pressure, we are going indirectly to the interior of the neutron star. And as I told you, at the surface, we have iron, right? In fact, we have an atmosphere and ocean, but this is a model for the atmosphere. This modeling is usually not included in the equation of state because the size is very small, 10 meters. But in the equation of state, we can include the outer crust, which is related to the chemical elements above iron. For instance, nickel 62, nickel 64, and krypton, and other uh, heavier elements. And this is reasonable, right? Because we have more energy, and this energy or density favors the appearance of other type of particles because the in medium energy is able to create these particles from the conditions. Okay, so you can see that, for instance, this inner crust here, where we have more or less degenerate neutron gas with protons and electrons, is more or less of the size of a 1 kilometer inside the star. Okay, so the idea would be to go to higher and higher chemical potentials and describe this mass radius relationship. And if we do that, in general, nuclear theories in this area, what they want to do is to draw this so-called phase diagram of the strong interaction matter. And this is a way to say that we are exploring the thermodynamics of nuclear matter. And the usual thermodynamic depends on the temperature and baryon density, or baryon chemical potential, and also the isospin asymmetry. And depending on the values of these parameters, we can have phase transitions, okay? For instance, in the early universe, we know that the densities were very low, but the temperatures were very high. And we know that these conditions could be have been repeated in many laboratories at CERN, or in other laboratories. But for this work, or for neutron stars, normally we focus on the sector of low temperatures, more or less 1 MeV, and the energy densities are about 1 times saturation density. And the idea would be to explore this transition from hadronic matter at low densities to quark matter. In principle, we can use quantum chromodynamics. All the degrees of freedom are in terms of color quarks and color gluons, and we can use this Lagrangian, which is famous in our area. And as we know also, this Lagrangian is quite complicated because it has these nonlinear terms between the gauge fields, this quadratic term, uh, which is at the power of 4 when the multiplication is done. And this is the Lagrangian, and if we use the thermal field theory, we can use the Euclidean version of that Lagrangian, and we can calculate the thermal partition function using this functional integration, where this side are the antifermionic and fermionic degrees of freedom, and the A mu for the gluons. So we have quarks, antiquarks, quarks, and gluons. And we could get the pressure in terms of the temperature and chemical potentials, depending on which degrees of freedom we are assuming, up, down, strange, or other heavier quarks. And for instance, this approach has been useful in lattice QCD, where they have performed Monte Carlo simulations for finite temperatures and low values of baryon chemical potential. And they obtain this plot, for instance, for the pressure and energy density and entropy, uh, entropy density for all these values of temperature. And these bands represent the results. So they also indicate some transition temperature, this crossover, because everything is continuous here. So this approach is useful. However, if we want to explore the dense sector of QCD using Monte Carlo simulations, there is the so-called fermionic sign problem, which avoids or forbids these Monte Carlo simulations. So there is nowadays many attempts to solve this problem. Even there are people trying to use quantum computing for this because nobody knows how to probe this sector. But fortunately, we have our first ab initio approaches, for instance, perturbative QCD, which works at ultra high densities, and also chiral effective theory, which works at low densities. Both approaches come from the QCD Lagrangian, so in some sense they are uh, ab initio. And here in this plot, what I wanted to show is that for the chiral effective theory, we have to calculate many Feynman diagrams. And also for perturbative QCD, it is quite complicated to calculate all these thermal Feynman diagrams. So we can have information at low densities and also at high densities. And the idea is to use effective approaches, which there are many in the literature. For instance, mean field theory or many varied techniques, or even this holographic ADS CFT correspondence and many other models. Okay, so in principle, we don't know how to solve this sector of intermediate energy densities or baryon densities. And okay, however, there is in the recent years a very strong interest on this quantity, the so-called trace anomaly for dense matter. And you know from quantum field theory that we can calculate this trace anomaly because the trace of the energy momentum tensor is not zero, but it has this form, and this result is valid even for the non-perturbative sector, and it depends on this beta function of QCD, the gauge coupling, these um, gluon fields, this anomalous dimension, and the quark condensate. In principle, if we can calculate the thermal average of this quantity, we could calculate how it behaves at finite densities, but as I told you, nobody knows how to calculate it at finite densities. So we can define it, make a guess for this quantity at finite baryon chemical potentials and temperatures and says that it has this form, epsilon minus 3p, because we know that we have a thermal conformal gas, or yes, a conformal gas, if epsilon is equal to 3p. So our gases, they will have uh, different behaviors of this quantity if they are close to the conformal limit or very far from the conformal limit. So in fact, it was proven in 2022 that this quantity delta, which is a kind of normalization of this trace anomaly, could be written only in terms of the pressure of energy density, but with this 1 over third. And we can analyze the extreme limits, for instance, a very stiff equation of a state or an equation of a state where the speed of sound is equal to the speed of light. And also we can consider a non-relativistic limit, and we can prove that this quantity, this delta, could only be between this minus 2 over 3 or 1 over 3 maximally. So the idea would be to know what is the range of values of this quantity in neutron stars, because it is the only system in nature where we can probe these high values of density. And for instance, this work of also Fujimoto and collaborators, they have calculated this quantity and they have proven that some data favor some negative region, and other approaches in doing interpolations between low densities chiral effective theory and high densities perturbative QCD favor, for instance, this red line, which tell us that this quantity trace anomaly is a little bit negative, but most of the time it is positive. So the idea would be to know what is the real behavior of this quantity. Nobody knows. And we can look for the behavior of this quantity in other contexts. For instance, as I told you, there are results for lattice QCD at finite temperatures, this purple curve, and you can see that this delta is positive, approaching PQCD. And there are also results for holographic quark matter using this ADS-CFT correspondence, this green line, and also is positive. And in fact, in this work, the authors, based on some data and some theories for the quark matter at intermediate densities, they have postulated that this quantity in neutron stars, this delta, should be positive definite, and they define this fitting function, this blue curve. And on the other hand, in 2023, there also appeared some results from lattice QCD, but not for baryon chemical potentials, but for isospin matter. And they have shown that this quantity could be negative. In fact, it is negative in a large sector of energy densities, and then it approaches also to perturbative QCD. So the question for us was to go beyond these results and not only assume that we have one phase stars. For instance, in this work, they were assuming that this quantity is more or less positive because they are only having nucleon degrees of freedom, and when the nucleon degrees of freedom are changed to quark degrees of freedom, they do that in a smooth manner, so the so-called crossover transition. However, as I told you some slides about, there are many works like this holographic Venetiano QCD model where they explore the transition boundaries at finite temperatures and finite energy densities, and they postulated that at least within their models, there could be critical endpoints and there could be first order transition lines. Okay, and if we go to the zero temperature case, which is the case of neutron stars, because the temperature is very low compared to the chemical potential, so it is a safe approximation to say that the temperature is low. And they found these equations of state, and the particular ones are these color ones, this blue, green, and red, dark red. And you can see here a kind of a constant sector. And these constant sectors are related to first order phase transitions. And when we solve the TOV equations for this mass radius diagram, you can find these values. Okay, they can surpass the two solar mass constraint and all other constraints for NICER, for instance. But at some moment, they start to display in this lines, okay, with positive slope. And it can be proven that these lines represent neutron stars with quark matter cores, but when you put these quark matter cores, these stars will be unstable and they will collapse to be black holes. So it is not clear which model should I use to produce stable neutron stars with stable quark cores. And for instance, stable quark cores mean that in the mass reduced diagram, we can have this uh, curve, which is decreasing in radius, it increases in mass, and then it begins to decrease in radius again. But after some point, it will increase again. And this increasing behavior could be associated with stable configuration. So this is a way I can put quark matter in these neutron stars in a stable manner. So, and the size of these quark cores is not very small, so we can have sizable contributions to the whole mass and radius. Okay, so usually we say that this is the first branch, the stable branch made of only hadronic matter, and this is the second branch made up of quark matter present at the core of these neutron stars. And usually these branches are separated by this unstable region. Okay. Okay, this is one part of the idea of twin stars. Okay, besides, the idea of twin star is that twins, okay, because we have two stars, for instance, here and here, with the same mass, but different radius. Okay, you can see here also. Here we can have a hadronic star composed only of nuclear matter. And we can have also a hybrid star with the same mass, but smaller radius. But you can see that the composition is different because now we have a quark core. So they are twins in the sense that they have the same gravitational mass, but a sizable value of different radius. Okay, so in that sense, they are twins. Okay, as you know, also since 2017, we have information from the gravitational waves coming from the merger of neutron stars in a binary system. Okay, we only know information of the in-spiral phase, but it is expected that maybe in the next 10 years we will have information about the merger itself and also the so-called ring down. And okay, after that, there are many processes, these gamma ray bursts, the kilonova, the afterglows, the collapse of this hypermassive neutron star into a black hole, etc. But the idea is that if we have information from this region, we can also know about the composition of these neutron stars, because as I told you, the main problem is to know what is the composition in these neutron stars, and if the composition at some moment changes from hadronic degrees of freedom to quark degrees of freedom. So this is the main question, and maybe using this gravitational wave data, we can extract that information. And this opens this so-called area neutron star asteroseismology. From we can extract information of how these neutron stars deform, for instance, before the merger, because you have the gravitational field of one neutron star affecting strongly the structure of the other neutron star, and these gravitational fields could activate non-radial modes, these so-called F mode, P mode, G modes, which are associated to different changes of shape of these neutron stars. And when these deformations want to approach the original form, they start to oscillate. And these oscillations are encoded in principle in this gravitational wave signal. And it is expected that in the future we can extract information from this for these independent modes. And if we know information from these non-radial modes, we can characterize or constrain the composition of this neutron star, and even we can know maybe if there are phase transitions within these neutron stars. So basically, the question for the whole talk, or the questions are these ones. What would be the behavior of this QCD trace anomaly in the cold and dense sector if we include phase transitions, strong phase transitions like the ones occurring in twin neutron stars? And the other question would be, does strong phase transitions leave unique imprints in these G modes? I'm going to talk about a little bit later about these G modes, gravity modes, which could be useful to be compared with future data. We will answer this with twin neutron stars. And for this, uh, let me remind you about twin stars. As I told you, two neutron stars with the same gravitational mass, but different radius. For instance, you can see here that this happens, as I already told you. But in this work of Jan-Erik Christian and Jürgen Schaffner-Bielik, they have postulated that we can classify all the possibilities of having twin neutron stars in these four categories, depending on the masses of the twin sector. For instance, here we have that the twin sector is about two solar masses, or here in this category too, the twin sector is below two solar masses, or, or the twin sector or hybrid sector could be between one and two solar masses, or below one solar mass. Okay, so we have broadly these four categories of twin stars. And here in the middle, you can see these blank regions, which are usually called unstable stars. Okay, and for instance, for our work, and as it is usually done in the literature, we have to separate the equation of state in two regions, one for the hadronic sector before the transition, before the critical pressure, and after the transitional pressure. And within this parametrization, so-called constant speed of sound, the speed of sound is a constant, and we can fix it. And we also have to satisfy this Seidov's criterion, which is necessary to have these usual unstable sectors. And for instance, only for completeness, I'm listing here the values of the transitional pressure, the energy density of the transition, the speed of sound, which I'm choosing between 0.5, which is reasonable, to go in and also go into the extreme case, which is the causal limit, 1. And also, you have to look at these values, which are in the energy density jump, which is this jump associated to the first order transition, and which are in these units, MeV over Fermi cube. And these values are large because most of the models consider more or less 50 MeV over Fermi cube or 80, but in all our categories of twin stars, we have to consider large values in order to have these four categories. We can plot the equation of state, pressure versus energy density. And as I told you, at low densities, we have chiral effective theory, and at high densities, we could have perturbative QCD. And for our approach of twin stars, we will have these sectors of constant pressure, and the strength of these transitions are associated to the size of these sectors of constant pressure. So larger sectors of constant pressure means that the transition will be strong and strong. And for the four categories for different colors. And also for the case of the gravity modes, I'm using similar ones. There are some technical differences, but basically they are the same. Okay, so now let's imagine that we have these four categories. Now we solve the Tolman-Oppenheimer-Volkoff equations, and we get information about the masses and radii. And after that, we can ask, okay, my twin stars, they are stable or unstable. So in order to answer that question, I have to solve these so-called Gondel-Rosinka equations, which are equations which depend on the solutions of the TOV equations, for instance, pressure and energy density, all in terms of the radial coordinate. But the idea is that these unknowns, this chi and this delta p, they are associated with the variations of the pressure when I am disturbing the whole star. So my whole star will oscillate like a harmonic oscillator, or it could favor the collapse of the whole star to be a black hole, and everything will be encoded in the behavior of this frequency square. And depending on the sign of this frequency square, I will say, okay, this star is stable or unstable. If this omega square is positive, then I will have harmonic oscillations of these stars. If this omega square is negative, it means that the frequency is a complex number, so it will favor an unstable configuration. Of course, from the macroscopic point of view, at the transition point between nuclear and quark matter, we will have also a lot of physics. And in principle, we have to use this theory so-called dynamics of phase transitions. And in this table, I'm listing many models to known about this microphysics, because this microphysics works very similar to the case of boiling water. You can have water, you can heat it, and then you will create bubbles of the new phase, bubbles of a gas. And these bubbles, they have what is called surface tension. And we know from all these theories that depending on the value of the surface tension, we can have a first order transition or a crossover transition. So here I'm listing only models for hadronic matter, and all this hadronic matter tell us that this surface tension, the sigma, is a very low number. And of course, we would need also information from the surface tension of the quark matter sector, but nobody knows how to calculate it. Lattice QCD also doesn't know how to calculate it. So basically, we can take one approach, which is suppose or assume a sector of values for sector, for the quark sector, or we can solve these models, right? But there are only few information about these models for the quark sector. So what we are going to do is to uh, assume two different things. We are going to assume only macroscopically that since this whole star is a fluid, we can focus only on the local fluid volume elements at the interface between the hadronic phase and the quark phase, and we can say, okay, we are going to disturb the whole star, and depending on the microphysics, we can have two extreme scenarios, which we call rapid and slow conversion scenarios, because in the rapid conversion, we can say that the microphysical time scale is very small compared to the oscillation period, the radial oscillation period of this star, which is more or less of the order of 1 millisecond. So if I consider this scenario, uh, this will affect the boundary conditions at the interface in these radial oscillation equations. On the other hand, I could say that while I'm stretching and squashing these volume elements close to the interface between phases, uh, we will have that the time scale for these uh, changes of phase from quark phase to the hadron phase, or the hadron phase to the quark phase, is very large compared to the oscillation period. So in that case, we will have continuity of these variables for the pressure and this chi variable, the variables from the radial oscillation equations. And okay, using these boundary conditions, we could say, okay, these neutron stars with first order phase transitions are unstable or not. Okay, this is part of the formalism for the radial oscillations. On the other hand, we have also the formalism for the non-radial oscillation sector, which could be related to these F modes, P modes, and other modes. And we have also to disturb the whole star, but that these perturbations should be done in a non-spherical manner, so we will have dependence also from the angles, from the phi and the theta. And we will have the spherical harmonics here, and we will also have these functions W and V, and we will also have variations in the for velocity, okay? We have to consider also variations in the conservation of the energy momentum tensor, okay? And the equations are very complicated for these perturbation equations, but we can simplify a little bit these non-radial oscillation equations, but using the so-called relativistic Cowling approximation, which means that we are not going to consider variations in the metric field, this G mu nu, it will be zero, so it will simplify the equations. And when we do that, our final equations are equations for these W functions and V functions. And again, we have also a non-radial frequency squared. And again, everything will be encoded in this omega square function. To solving these equations, we need the solutions of the TOV equations, of course. And since we have a strong first transition, we will have also to impose boundary conditions for these functions, okay, at the interface. This plus and this minus are related to the fact that I'm saying something about continuity before the transition and after the transition, okay, and also for these V functions. And again, we have here the presence of this non-radial frequency. Okay, so I will pass to the result because we now have the formalism for the radial oscillations, for the equations of state, for the non-radial oscillations, and all that. So we are ready to explore these quantities. And this main quantity will be the trace anomaly in this first part. And for this trace anomaly, I could solve it analytically, in fact, for the case, for instance, at the transition point, where I told you that the pressure is a constant, and if the pressure is a constant, this is the definition of the speed of sound squared in terms of the derivative of the pressure in terms of the energy density. And if the pressure is constant at the transition point, this derivative is zero, so we can solve an equation for this delta because the authors, Fujimoto and others, have separated the speed of sound in two terms, a derivative and a non-derivative because they depend or not on the derivative of the trace anomaly. So we can solve at the transition point, and we can also solve in the quark phase because, as I told you, we are using the CSS parametrization where the speed of sound is a constant. So we can have this analytic expression. And for this trace anomaly, I will focus only in the category 2 twin stars because they display the strongest value of energy density jump. And first, we can solve the TOV equations. We can plot the mass radius diagram. Here we have the black curve is related to the hadronic branch. And then if we impose the rapid boundary conditions at the interface, we will have unstable configurations. Here the dots, which are smaller compared to the other circles. And we will have that we have unstable configurations, and then after some point, these configurations will become stable again, okay, but only at the end of these curves. And you can see here as a gradient of colors, the behavior of this trace anomaly. And you can see that at the beginning of the transition, this quantity is positive. But as we go to the twin sector, this quantity decreases and it approaches a negative value. And if we plot this quantity delta versus epsilon, we can have this black line related to the hadronic branch. Then, for instance, you can have this field circle in black, and the transition, as I told you, the first order transition occurs with an energy density jump. So we are going to jump from this value to this value here to the other circle. And then we have unstable configurations, as I showed you in the mass radius diagram. And then we recover these continuous lines, which are related to stable configurations. So we will have lower and lower values of this trace anomaly. And We have tested this for many configurations, for many families, and you can see that most of them approaches this negative sector, in contrast to these results of Fujimoto. Also, we can consider the other case, the slow conversion case, where the boundary conditions at the interface are continuous for the radial oscillation equations, and we have the hadronic branch, and as soon as the transition occurs, we have all these families of stars which are stable. So we have here stable, 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 until we go to lower values. You know that in the background there are bands, red bands, green bands. All these are data, right? Astrophysical data. So most of our results pass through these bands of data. And you can also see that this quantity, this trace anomaly, starts being positive, but it goes to be negative. Okay, even a little bit negative than the other case. And you can see here again the hadronic sector, the energy density jump, and then a decreasing, but here we don't have unstable configurations. All of them are stable. And this stars with the highest slope. They represent twin stars with a value of speed of sound equal to 1, so the causal limit. Okay, if we reduce this extreme limit, we can have these darker red curves with a value of 0.5 times the speed of sound. So you can see that the slope is less pronounced, and the values also, they are a little bit negative, not as negative as the extreme limit of the causal equation of state. So this is a good comparison. And in fact, somewhat recently, some months ago, this group also in Frankfurt, they have just this macroscopic Veneziano QCD model. They also combine it with this van der Waals equation of state for the hadronic sector and all that. And I calculated this trace anomaly in terms of the baryon density, and you can see a similar behavior. So you can have a hadronic branch, and then it jumps to this quark sector, and then it decreases again. The only difference is that in their studies, they have forced their results to approach perturbative QCD. For our case, this was different. We didn't want to force our parameters to approach, but of course, this recent result complements our assumptions. And usually, what is said in these original works, they say that this delta should be positive, because as we go to higher densities, we are having an increasing number of degrees of freedom. However, they didn't consider phase transitions, and first order phase transition, as is usual, should be related to a finite value of latent heat. So if we calculate the latent heat for our transition, it is directly related to the trace anomaly. And in fact, we can prove that this latent heat is related not only with the changes in the number of degrees of freedom, but it also in the discontinuity added at the transition point for an increasing number of degrees of freedom. So it is more generic, but of course, in the case of a smooth transition, Q would be 0, so the number of degrees of freedom would follow a smooth behavior. So this is something to be noticed. And okay, this is one part for the trace anomaly. Now I'm going to talk about the G mode. Okay, and I want to warn you that if you go to the literature, you will see a lot of information about the G mode. But in contrast to that, to those results, this study is focused on the so-called discontinuous G modes, because usually the classical G modes are related to the changes in the composition, because as we go to higher densities, new degrees of freedom could appear, like hyperons, for instance. So how these new appearance of degrees of freedoms affect the G mode, or the way the star deforms, this is encoded in the G mode. However, these G modes are called discontinuity because they are directly related to the energy density jump or the latent heat. There are also in the literature these so-called interface modes, which are more focused on this transition between the cross of the neutron star to the core. And this occurs at low densities. And as I told you, our transitions occurs at more or less high densities. So Please don't confuse the interface modes and the classical G modes. For our case, we will only call this discontinuity G modes. And also, in 2020, Toneto and Lugones in São Paulo, they proved that if we want to calculate these discontinuity G modes for rapid conversions, the frequencies will be zero. And this is because as everything happens very fastly compared to the oscillation time scales, these discontinuity GMOs will be equilibrated too fast, so they will not have any imprint in the gravitational wave signal. So the rapid conversion case should not be considered, so we have to focus only in the slow conversion case. And for instance, as we can show first the behavior of the mass radius diagram of category 1 slow twin stars. And as I told you, this category 1 is related to hybrid star families above the 2 solar mass constraint. And here I'm showing only one of them, not all of them, in order to be clear. And okay, all these stars are the slow hybrid stars. And these stars indicate the maximally stable configuration, or the maximally stable configuration. And we can calculate the frequency of these discontinuity G modes, for instance, in terms of the gravitational mass or frequency in terms of the tidal deformability. This quantity is associated to how one star is deformed in the presence of the other. Okay, so in a binary system, for instance, in this gravitational wave event GW170817, they have extracted values for this quantity. And we can see here these different behaviors for this frequency, this discontinuity G mode frequency. And all this behavior is related to the behavior of the solutions in the mass radius diagram. And interestingly, you can have that, for instance, there are these slow stable twins where we can have two configurations, for instance, here and the other one. Both have the same gravitational mass, but they have different G mode frequencies. So if in the future LIGO detects this kind of behavior, two different frequencies, G mode frequencies for the same gravitational mass, so it could be an indication of first order phase transition. And we can say the same for the other families. We can go to the extreme sector where the category 2 slow twin stars, where all these stars are again stable. And in this case, the jump in the energy density is very large. And we can calculate the frequencies for the G mode. And we can see here that the frequencies, they increase very much because in this case, for category 1, the values go from 1.45 to more or less 1.6. But in this case, I'm going from 2 to 5 kilohertz. Okay, so this is a quite distinct behavior. And this behavior is not usually found in the literature because, as I told you, the rapid conversions should be discarded. And in the slow conversions, we find these large values. Also, the behavior in the frequency versus tidal deformability is different compared to the above case, right? And here you can see also a quantity called compactness, M over R, in geometrical units. And it will tell us how compact are these stars. And this value should approach the so-called Bookta limit, which would be a value of M over R of more or less 0.4. So if we don't have those values, we are fine. We are not breaking any law of physics. Okay, now we can go for category 3, slow twin stars. And we have these families again. You can see that, for instance, here I have the hadronic branch, then the usual unstable, but for slow conversions, all these stars are stable. And we can see a kind of separation of families here, depending on the transition. You can see here that some maximal configurations approach 2.5 solar masses, while the others approach low values. And we can see here the different behavior in this plane, frequency versus mass. So this is a quite distinct behavior. And again, the stars indicate the maximally stable configuration. Also, we plot the compactness. And we can go to the category 4 slow twin stars. And in this case, you remember that the transition, this discontinuous behavior occurs at masses below 1 solar mass. And again, all the hybrid configurations will surpass the 2 solar mass limit. And the stars will indicate the maximal stable configurations. And we can see also that we can have some kind of many stars with the same gravitational mass and a little distinct values for the frequencies. Okay, so but in this case the behavior is decreasing. And also there is a distinct behavior in the frequency versus tidal deformability. And we can plot what is the behavior of this tidal deformability in terms of the gravitational mass. And usually, if you go to the literature, most of the hybrid stars, they focus on this category twin, category 3, twin stars or hybrid stars, where the behavior is more or less decreasing, okay? But you can see that the other categories, they show quite distinct behaviors. And only for comparison, we have put here a value for the tidal deformability of a canonical neutron star, 1.4 solar masses. Just for comparison, our parameters were not adjusted to satisfy this data. And globally, we can compare the behavior of this frequency in terms of the mass. And you can see here that the category 2 twin stars, slow twin stars, they are quite distinct, not only qualitatively, but also quantitatively because of the large values. And this makes these categories more interesting because it is expected that LIGO in the next 10 years will have more, they will reach a stage of detecting signals with larger frequencies. So maybe we can, in the future, they will detect regions like this. And normally these twin stars, they favor low values or of frequencies. But in our 4 categories, we can see that they are about 1.5 kilohertz. And for instance, comparing to the work of Toneto and Lugones, where they also explore hybrid stars in the slow conversion scenario. For instance, they have their mass radius relation here. You have again the hadronic branch, and then these lines are related to the usually
Oh dear, we've had a problem since our speaker just lost his connection. We might want to wait a little bit for him to finish.
Yes.
Roberto, this is your time for your juggling act.
It's gonna connect soon, for sure. Maybe
We might want to wait for a couple minutes and then we'll see. It's a shame it was just at the end.
at the end.
So please everybody, please stay tuned for a couple minutes. See if
Yeah.
if
At
we
some
can
point, I thought was my internet connection.
Yeah, I thought so too. But no. Yeah. No, but this last part is very interesting. So in principle, they have the 2 twin neutron stars, and then they're merging and they're emitting these gravitational waves, and then the information carried by the gravitational wave depends on the phase of each neutron star. This is quite interesting, if I understood correctly, because this is this is quite
You have to
beyond my
wait
expertise.
for Jose for
For the clarifications.
the clarification, right?
Yeah, this is very good. Let's give him some time.
Yeah, I don't know. I mean, the important stuff that he realized that his internet
I
got.
will send him an email. Give me a second.
Yes. I want to stay here looking to the people in YouTube watching us for some minutes. Yeah. Yeah, for the moment I can say that the next webinar, beside the one that we have today, is in 2 weeks more. And it's gonna be Lena Murchikova. Soon we are gonna know the title of the talk. This is on 26. Jose is back. 26th of November.
Right, I just sent him an email.
Yes.
Hello, welcome
Okay,
back.
sorry for the sorry for the problem.
We were starting. We're going to start to dance to entertain the audience.
Okay, sorry. I'm going to share. Okay,
Yeah,
I'm
go ahead. Go ahead.
about to finish. I don't know. Okay, can you see my screen?
Yes.
Okay, so I was saying that in this work of Toneto and Lugones, what they usually do is calculate this frequency for the G mode, and you can see that in all these hybrid configurations, the values of the frequencies are below 2 kilohertz, and the behavior is more or less monotonic. So this is quite different to our case in this left panel. And because you can see that there are some configurations where you can have the same gravitational mass and two values of frequencies, or even here. Okay, so this generalize their findings. And okay, the final part, this ending part, is related to the so-called universal relations. A universal relation is a way to relate some quantity, which could be inferred potentially in the future, to some quantity which is associated to the microphysics. Okay, for instance, in this case, I'm showing an example of a universal relation between the frequency of the fundamental mode, which is also a type of non-radial mode, in terms of this average density, m over r cubed. And if in the future this frequency is measured, we could have a range of values or one value for this m over q over r cubed. And for instance, here we have all these color lines, which are different equations of a state. And these guys, they made a kind of fitting procedure, and they found this relation between this frequency and this so-called average density, and more or less containing all the global behavior and more or less the numerical behavior too. So the idea is that if in the future we extract information from the fundamental mode, we can constrain these values of m over r cubed because they come directly from the equation of a state through the TOV equations. So we were thinking if we can do that also for these twin stars and for the four categories of twin stars. And we tried many types of universal relations. For instance, we also tried things like this or many other known in the literature. And we found that our best fit relating quantities associated to the frequency of the G mode to quantities associated to the transition density, which is a way to say that these neutron stars have transitions, we have this kind of linear fitting where m is the mass normalized by the mass of a canonical neutron star, the radius also normalized by the canonical value of a neutron star of that mass also the tidal deformability, which is more or less in this order of 10 to 3. And we can say that in the future, LIGO or other observatories are able to measure this FG, and more or less from the same measurement, they could extract values of lambda and values of m and r. We can extract this quantity, this delta epsilon, divided by some quantity, which is a kind of normalization. If we can extract this value, we can infer in principle if the neutron stars observed have very large or small values of energy density jump, which, as I told you, if they are large, they are indicating us that there is a strong phase transition within the neutron star, and basically this could be a transition to quark matter. Okay, there are a lot of details in this quark matter phase, but the basic quantity is this, because we can go to a hadronic phase, no, to a quark phase only composed of quarks up, down, and strange with weak interactions, or maybe including the presence of a color superconducting phase or other interaction channels. So we found that this universal relation is valid for our 4 categories of twin stars, and hopefully maybe in the future will be useful, because now LIGO is using this kind of universal relations like this one to infer information from this event GW170870. Okay, so as a summary, we found for delta, for this normalized trace anomaly, an abrupt decreasing trend to negative values, because the quark phase is very stiff, and in order to prove this, we explore the case of speed of sound 0.5 and also 1, which is the causal limit. And in the case of the causal limit, which is the extreme limit, we have the delta is negative, even reaching these very low values. And if you go to the literature, most of these values of delta are considered only to be negative, but for instance, minus 0.1 maximally. It's difficult to reach this. So twin stars are in a way a laboratory to study first order phase transitions. And on the other hand, for the discontinuous G mode, we found sizable differences for each category related to these energy density jumps. We propose a kind of universal relation, which could be useful in the future, and of course could be improved also, because for the quark phase, we can include a realistic equation of a state where we can have control on the interactions at the Lagrangian level and all that. But this was more or less a parametric study in order to prove what maximally can happen. And in the next decade, through LIGO and other observatories, the Einstein telescope, LISA, and all that, it is potentially plausible that multimessenger astrophysics will provide us to look into the microphysics of nuclear matter in these extreme conditions, which is our fundamental task as nuclear theorists and in general as astrophysicists. And I would like to finish acknowledging CNPq from Brazil, which is funding this research. So that's it.
Thank you very much, Jose. It's been a fantastic talk. It's been a lot of information. It's been very thorough, very thorough. Unfortunately, we don't have that much time since we usually finish more or less at this time. But let's extend it a little bit so we can ask questions. No problem. We also had the problem of the disconnection. So first, just to make sure that I understood everything, right? So in principle, you notice that you have these 2 scenarios with these curves, where you have stars that have got the equal mass, but they have different size, right? So in principle, these 2 scenarios could be due to a different internal structure given by this by the fact of having a quark core or not, right? Now, what I'm not sure if I understood correctly is this connection with the gravitational waves. So are these 2 stars that have got a different internal structure merging and then emitting a gravitational wave? Is that the situation that you're describing? This is what I did not completely understand.
Okay, okay, yes, 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 that is a valid question. And the idea is that for this G mode, at least one of them should have a discontinuity in a binary system, not both, only one of them. Because
Okay.
if there is no, if both are hadronic, there will be no discontinuous G mode, but there will be a kind of signal coming only from one. And if you have both of them, it could be increased, the signal. So we have to look a kind of superposition of both frequencies. But at least for our case, we were assuming that only one of them in the binary system could have this discontinuity.
I see. I see. Okay. Okay. So not so bad. All right. Super. I don't know, Roberto, if you have any questions.
Yes, but it's similar to the one in YouTube.
Oh,
It's,
there's one in YouTube.
there is one in
Oh,
YouTube.
yeah, super. Okay, so I'll pass it on. Thanks for letting me know. So the question comes from Andres Gomez. He says, thanks for the presentation, very interesting. I have a naive question. The theta angle of QCD is considered in the anomaly, or is it not?
No, no, no. It's not considered. As you know, this theta angle is very small, and there are people many years ago who has explored how important could it be at finite densities, and they have proven that this quantity will not give any contribution at high densities. It could give a contribution at large temperatures, but this is another scenario like the primordial universe. But for us, no, it will not give any contribution.
Super. There is usually a lag between our transmission and the questions. So we can ask a couple more questions before Andres responds. So Roberto, is that okay with you, or would you like to ask something else?
No, yeah, it's okay.
Okay. So I have a question regarding so something nice is that you have your curves for mass and radius, and you contrast it with experiment, right? Initially, you show the nicer experiment. So my question is, how do these experiments probe this internal structure of the neutron stars? I mean, what is it that they actually measure to get an idea of what is the mass, what is the radius?
Okay, okay. In the case of the mass, there is a kind of test of general relativity called the Shapiro delay. The idea of the Shapiro delay is that if you have a binary system, for instance, two neutron stars, this neutron star will emit radiation. And when this radiation is in the direction of Earth, this radiation should pass in the presence of the gravitational field of the other neutron star. So this gravitational field will create a kind of delay, a kind of redshift in the signal. So this is a kind of precision test, and you can extract indirectly the mass of the source
This is
comparing the signal.
fantastic. I
Yeah,
had,
yeah.
didn't have the faintest idea this was possible. Okay.
Yeah. So this is for the case of the mass, the Shapiro delay, which is very famous, and it proves also the consistency of GR until now. On the other hand, for NICER, what they do is that in these neutron stars, they have what is called hot spots. So some hot regions in the surface of the neutron star that, since the neutron star is rotating and it is emitting some pulses, this information that arrives to the Earth, they will have again also a kind of delay, and you can compare a kind of delay between the surface without a hotspot and the surface with the hotspot. And this delay again is associated to the source. and you can model it as a sphere, and you can say, okay, the size of the source should be of this size in order to have this value of redshift 2. Basically, this is the idea. But this is in the range of the X-rays.
Okay. Okay, very nice. Very
So
nice.
this is the way that astronomers do. But nowadays, also there is a lot of interest in heavy ion physics. So heavy ion physics, they also have a lot of experiments, and they also constrain the equation of a state, okay, at low densities, but they constrain it. And they are focusing mainly on these canonical neutron stars because the densities are not too high. And they have data, for instance, new data about the so-called neutron skin, which is a kind of skin for the neutrons, and it will affect directly the parameters in the Lagrangian. And so if you have a value of radius, you can constrain the parameters in your model, and you can say, okay, I could even constrain more my parameters by having results for the masses and all that. So kind of you get information from the heavy ion sector, you combine it with astrophysics, and then you improve your model, and you again go to heavy ion physics to contrast it with some state-of-the-art heavy ion data because nowadays there are more and more information on that.
Very nice. Very nice. No, it's impressive when you said, oh yeah, these are constraints from observations and they all fit the curves. It was very, very nice. There's a response by Andres Gomez. He's asking if this first order phase transition can contribute to the stochastic gravitational wave spectrum measure for nanograph.
Yeah. Okay. In these binary systems, what we have is very old neutron stars, which they are orbiting one to the other millions and millions of years. But the idea is that this first order phase transition could also happen in other scenario, the so-called supernovas. And in supernovas, you can have that in the gravitational collapse or the so-called protoneutron star phase, you can have the collapse of all the outer layers of matter, they can compress even more the newly born neutron star. And if the equation of state allows it, okay, you will have a first order phase transition because you are assuming that it has. And it has been proven that there will be other types of non-radial models, and this is more complex because in that scenario, we are adding also the effect of temperature. Temperature could serve usually to soften the strength of the first order transition. So the idea is that yes, even if the temperature softens the strength of the first order phase transition, the signal is quite evident, and in the future, nanograph could detect the presence. Okay, this is more complex because the temperature generalized the equation of state. For me, equation of state only means pressure in terms of energy density, but if you add temperature, you will have a three-dimensional equation of state because your equation of state will depend on the baryon density, on the temperature, and on the fraction of protons. So this will be more complex, but there are people, okay, working on that because also the simulations for supernovas are far more complex. And in principle, yes, basic answer.
Great. Okay, so we really should stop now, given the time. So we'd like to thank you, Jose, for this very, very nice talk. And we'd like to thank all of the questions given by our viewers. And we'd like to remind you that in 2 weeks' time, we have another webinar, as usual. Roberto gave you the details during the break. So we'll see you in 2 weeks' time. And Andres says that thanks for the answer. It was all very clear. Okay.
Thank you.
So thank everybody. Bye bye. Okay, we're offline. Muy
Okay.
bien. Ay,
Muy
excelente.